Hi everyone, my name is Megan Flynn and I will be covering the second section of Chapter 2 of our Biology 2E Openstax free textbook. So that textbook can be accessed with the link down below, so openstax.org/books/biology 2E pages. So I've already discussed section 2.1 in a previous video, so if you haven't had a chance, please watch that video. Click that subscribe button so it's easy to access those previous videos. This video just covers the section 2.2 of chapter 2. So in the first part of chapter 2, we learned a little bit of chemistry. So we learned what the atoms are, how atoms form molecules. So now we're going to concentrate on the water molecule. So the water molecule being one of those, chemical foundations of life. So here are our learning objectives. Always a good idea to write these down. I'll be covering each one of these learning objectives in this video, and then at the end of the video, revisit them and see if you can address them just from what you learned from this video. And if not, go back into that Openstax textbook, that free textbook, and see if you can review it a little bit more in detail with that textbook. So here are our learning objectives. By the end of this video, you should be able to describe the properties of water that are critical to maintaining life. You should be able to explain why water is an excellent solvent. Provide examples of water's cohesive and adhesive properties, as well as discuss the role of acids, bases, and buffers in homeostasis. Hey, we learned about homeostasis in chapter 1. So if you don't know that term, head back and watch my chapter 1 video. All right, so let's start out by looking at our water molecule. So from the previous video, 2.1, we learned that water molecules are held together by polar covalent bonds. So that means that the oxygen and the two hydrogen atoms are held together with a polar covalent bond. If we have a polar covalent bond, because this is a water molecule, you can see that we have kind of a partially negative end of the oxygen atom in this molecule and a partially positive end on the hydrogen ends of this water molecule. And because of this kind of polarity that's involved here, we end up having water and other substances that also form polar covalent bonds tend to be more hydrophilic. Okay, so if we have a partially negative, partially positive end of a polar molecule, it tends to want to react or interact with water. So it tends to be hydrophilic. So hydro means water, philic means liking or loving. So molecules that have polar covalent bonds tend to be hydrophilic. If we're talking about non-polar molecules or molecules where they're forming non-polar covalent bond, they equally share those electrons, they tend to not want to be around water. Okay, so they are hydrophobic. So hydrophobic, hydro means water, phobic means fearing. So they're going to be kind of stay away from that. Some examples of that would be, for example, if you take vegetable oil and put it in water, you'll notice that there's a separate layer. The oil does not want to interact with the water itself, so it forms that kind of layer. And because that oil is nonpolar, it's made up of nonpolar molecules, it's going to basically react by staying away from that water. It's not going to dissolve within it. When we talk about water, we can think about water in 3 different states. Okay, so water can be in a gas state as steam or water vapor. It can be in a liquid state as liquid water that you might drink, or it could be a solid state meaning ice. Okay. And what's interesting about these 3 different states the bonding between two water molecules, they will form what's called a hydrogen bond. Okay. So we know that nonpolar compounds, they're not going to want to interact with water molecules, but polar compounds or polar molecules do. Now what's interesting about water is that even though they're held together by polar covalent bonds, they, because of that partially positive and partially negative end, they will form hydrogen bonds with each other. So between two water molecules, the partially negative end of oxygen and the partially positive end of a nearby water molecule will form a temporary bond known as a hydrogen bond. Now this plays a role when we think about water's different states, the gas state versus the liquid state versus the solid state. So when we're looking at water at the liquid state, it's liquid because water molecules are constantly forming and breaking hydrogen bonds with nearby water molecules. So that makes it more of a liquid form. When we have our more steam or gas state of water or water vapor, we see those hydrogen bonds breaking and reforming, but at a more further state. So they'll be breaking those bonds and moving further apart from one another. When we start seeing the temperature drop, the water molecules will, form those hydrogen bonds with each other, but those hydrogen bonds will, because of the temperature being colder, the molecules are not going to be moving as fast. And so we'll see those hydrogen bonds remaining intact longer. And when they're becoming intact longer, we'll notice that they become more spread out into this lattice or crystalline shape. And because of that, we end up seeing water molecules, solid water, ice, becoming less dense than liquid water that are more closer together, forming and reforming those hydrogen bonds. So let's watch that animation here. So if we take a look at ice, you can see how we have the hydrogen bonds between the hydrogen of one water molecule and a nearby oxygen of another water molecule nearby. And so because the molecules have slowed so much because of the cold temperature, they are kind of stuck in this lattice structure. And so they're more further apart than if it's liquid, where they're constantly breaking and reforming these hydrogen bonds, and so they could be closer or further apart over and over again. So we end up with this lattice structure, which makes ice less dense than liquid. Okay, so the solid form of water is going to be less dense than the liquid form of water. So that's something that's kind of unique with our water, and makes it, why water is a unique requirement for life. And that allows ice to float on top of liquid water. Okay. Another property of water that helps with our living things is that water has a high specific heat capacity. So specific heat capacity is the amount of heat 1 gram of a substance absorb or lose to change its temperature by 1 degree Celsius. Now water, it has a very high specific heat capacity of any other liquid. So that means it takes a lot of energy to break those water bonds, the hydrogen bonds between, or the water bonds, in order for it to vaporize. Okay, so that high specific heat takes quite a bit of heat in order for us to change water from the liquid form to the gas form. So, you can tell this by if you've ever had to wait for water to boil. seems like it takes forever, okay? See, it takes quite a while for water to start heating up to the point where it will steam, okay? And that's due to water's high specific heat. A calorie, by the way, is the amount of heat required to change the temperature of 1 gram of water by 1 degree Celsius, okay? So in order for our water to increase, 1 gram of water to increase from, say 99 degrees to 100 degrees Celsius, that would require 1 calorie of heat. So heat is just a calorie is just a unit of energy. In addition to water's high specific heat, it also has a high heat of vaporization. So that means that the amount of energy required to change 1 gram of liquid water to 1 gram of gas, it's going to take a lot of energy to do that. So in this case, it takes about 586 calories required for water to transform from a liquid to gas state. Some of you already know that the boiling point of water is 100 degrees Celsius, the freezing point being 0 degrees Celsius. So heat is able, at 100 degrees Celsius, that amount of heat is able to break those hydrogen bonds between the water molecules. And when those hydrogen bonds are broken, that allows kinetic energy between the water molecules, allows the water molecules to escape from a liquid to a gas or evaporation form. Okay, so you can tell here in this case, the liquid in this cup must be, at a point where the hydrogen bonds are breaking between the water molecules and allowing for individual water molecules to escape in a vapor. Another interesting property of water is its solvent property. So water being polar, it has that slightly positive end to it and a slightly negative end to it. And because of that, it becomes a universal solvent. So a solvent is a substance capable of dissolving other polar molecules and ionic compounds. So water is the universal solvent because it has that polarity involved. So that's the slightly positive hydrogen end of the water molecule versus the slightly positive negative end, or slightly negative end of the partially negative end of the water molecule makes that polar. And because of that, it's going to be the universal solvent where molecules that are partially positive or partially negative or positive or negative are going to be more attracted to it. So we can see here, for example, we see what's called a sphere of hydration, in which a polar water molecule surrounds charged or polar molecules, thus keeping them dissolved. So here we have a chlorine ion. So NaCl, by the way, is table salt, and it's just that ionic bond that holds a sodium and a chlorine atom together. Remember, ionic bonds are weak bonds. So when we put salt in water, the water being the solvent, the water molecule will kind of surround. Water molecules will surround the the chlorine, because it would be more charged because it's gained an electron, and then the sodium ion, the negative, partially negative end of the water molecule will kind of form a sphere of hydration around that sodium ion. Dissociation is the release of an ion from a molecule. Okay, so for example, we have our table salt. Once it's dissolved in the water, okay, they're no longer together. You see sodium over here surrounded by water molecules. You see chlorine over here, a chlorine ion over here surrounded by hydrogen or water molecules. So it's been dissociated. Another unique property of water is that it has cohesive and adhesive properties. So cohesion is when we have water molecules attracted to each other. And that attraction allows them to kind of stick together. So water, if we think about like the surface of water, we have water molecules are close together where they adhere to each other. And so when water is adhering to each other, its cohesion is causing that. And that is what is where we end up with something called surface tension. So surface tension is where we have a body of a liquid that prevents molecules from separating. So if you take some water and something very light in weight, such as a needle, and lay it carefully across the water, instead of the needle sinking into the water, it might float right on top. And because of that surface tension, the water's cohesive ability to kind of stick to each other allows that, prevents that needle from breaking the surface and dropping into the water itself. Okay. So surface tension is due to the cohesive nature of water. Adhesion is another property of water where water tends to cling to nearby surfaces. So for example, if you take a look at, if you just have like a glass of water or something like that, you'll notice that the edges of the water, okay, it's not going to be horizontal. You'll see it kind of stick a little bit more to one side and the other side. And that's because the water has these adhesive forces where it's attracted to the side of the beaker or the glass that you're talking about. And so this will actually become useful in plants and other organisms where the adhesiveness of water wanting to cling to the sides, as well as the cohesiveness of water molecules clinging to each other, can help draw water against gravity up into, for example, a tree. And so that's called capillary action, where if we have narrow tubes, such as in a tree we have xylem, which is these little narrow tubes within the tree, the cohesiveness of water is going to want to have water stick together, but the adhesiveness of water wants it also to cling to the sides of that tube, or say xylem or so forth. So it kind of draws water up against gravity. Okay, so that's kind of a unique property of water. So the combination of water's cohesive and adhesive properties, that can be very useful for life. For example, with our trees, allowing water to move against gravity up into the trunk of the tree, out into the branches. Trees, they don't have hearts like we do to pump things. So this is a way that they can get water to the leaves in order to do photosynthesis. Here's another example. We have the cohesiveness of water clinging together creates surface tension, and the adhesive nature of water with the toe pads of this little water strider, where it's adhering to the surface. So this little water strider can actually, walk across the water and no problem staying afloat. So it's not going to actually go into the water like if you floated on top of the water, it's still going to push you down. So another part of, actually I think it's the last part of this chapter, gets into pH. Okay, so pH buffers acids and bases. So we'll talk about this in relation to water. But first, let's just kind of define what an acid is versus a base. So an acid is a molecule that donates hydrogen ions and increases the concentration of hydrogen ions in a solution. So when we have something like anything that's acid, so HCl, hydrochloric acid, when we place HCl into water, for example, it's going to donate hydrogen ions to that solution, that water plus the HCl to that solution, which increases the amount of hydrogen ions in the solution, making it more acidic. A base is a molecule that donates hydroxide ions, or otherwise binds to excess hydrogen ions, thus increasing or decreasing the hydrogen ions concentration in the solution. Okay. So basically, we're going to talk about acids and bases in relation to our pH scale. So here's our pH scale. So pH scale goes from 0 to 14, and it is a measure of the hydrogen concentration within the solution. So the higher the hydrogen concentration there is, the more acidic it will be, which is going to be a lower number on our pH scale. The lower the hydrogen ion concentration there is, the more basic or alkaline it will be, or the higher the number on the pH scale. Okay, so when we're looking at figuring out the pH scale, if we want to figure out if it's an acid or a base or if it's neutral, we have to look at the concentration of hydrogen ions to hydroxyl ions. So if the concentration of hydrogen ions is greater than the concentration of hydroxyl or OH negative ions, then we consider it acidic because it's less than 7 on the pH scale. If the hydrogen ion concentration is less than the concentration of hydroxyl ions, that means that it's going to be basic or greater than 7 on our pH scale. If the hydrogen ion concentration is equal to the concentration of hydroxide ions, then we consider that neutral or pH 7. So just looking at this chart, you can see some of the everyday items that you might have in your household and kind of see where they land on the pH scale. So for example, if you drink some orange juice for breakfast, orange juice is going to be acidic, meaning that there's a higher concentration of hydrogen ions in orange juice compared to hydroxyl ions. If you're doing laundry and you have some soapy water in your laundry machine, or your washing machine, then that soapy water actually has a greater concentration of hydroxyl ions to hydrogen ions, making it more basic. Another thing when we're dealing with the pH scale is that it's a logarithmic scale. So that means every time we move up or down our pH scale by 1, we're actually increasing or decreasing the concentration of hydrogen ions by a factor of 10. So that means that, for example, baking soda at pH 9 compared to milk of magnesia pH of 10, baking soda actually has 10 times higher concentration of hydrogen ions than milk of magnesium. Okay? So if we're going from, say, pH 5 to pH 3, black coffee compared to orange juice actually has 100 times higher concentration of hydrogen ions to black coffee, because each of these is a factor of 10, base 10 scale. Okay, so it's a logarithmic scale. So black coffee has 10 times more hydroxyl ions compared to tomato juice. Tomato juice has 10 times more hydroxyl ions than orange juice. So 10 times 10 means that black coffee to orange juice has 100 times more hydroxyl ions compared to orange juice. Orange juice has 100 times more hydrogen ions compared to black coffee. So it's a logarithmic scale. So each time you're moving up or down the scale, it's a factor of 10. So let's watch a video to help us understand this a little bit better.
Hi, this is Jamie Davis, the Pod Medic, and we're talking about acid-base balance today. Understanding pH, specifically in this installment. What is pH? So what is pH? Well, pH stands for the measurement of hydrogen ions present in a particular substance. That hydrogen ion concentration, P percentage hydrogen. So that's what pH stands for. One of the things that messes people up about pH, though, is that it is an inverse logarithm. So let's talk about this for a minute. Inverse logarithm, what's that mean? Logarithm is a scale where each time you increase by a factor, it increases by 10 times. So if you go from a pH of 7 to a pH of 8, it is 10 times more alkaline at a pH of 8 than it is at 7. And this continues all the way up the scale. Other things that are logarithmic scales, we have logarithmic scales for the Richter scale. This is the measurement of the severity of an earthquake. That means that an earthquake that is measuring 6 on the Richter scale is 10 times stronger than an earthquake measuring 5 on the Richter scale. So this is what a logarithmic scale does. pH is really confusing, though, because it's an inverse logarithm. As the percentage of hydrogen ions increases, the number on the pH scale goes down. And this is what messes people up. When something is more acidic, it has a lower pH. It doesn't make sense, and it doesn't mean a whole lot to those of us that are trying to memorize this stuff, but that's what causes issues. So what is the safe pH range in a human being? Generally accepted, the numbers are 7.35 to 7.45 pH, and that means that we're slightly alkaline. We aren't very acidic. We like to be right around normal, above, or a little bit above normal, because that's the way our systems are. We like to be buffered and against acidity, and so we try to fight against acidosis in our homeostasis. So I came up with this seesaw thing to help you understand how pH works. You'll see on the left-hand side the pH scale going from 1 up to 14. 7 is normal. Anything higher than 7 is considered alkaline. Everything lower than 7 is considered acidic. So you have this scale. And you can see that if you use a seesaw, this visual will help you understand that as the number goes lower, the acidity increases, and consequently, as the number goes higher, it becomes more basic or more alkaline. And you can see that illustrated here. So remember this seesaw when you're thinking about pH, and it will help you get a handle on the pH system. Here's a look at our references for this particular short segment on pH. And if you'd like to find out more information, you can head over to medicast.com or find the great student resources available at medicastextra.com. This has been a Medicast Podcast Extra production.
Okay, so we're going to talk about buffers. In that video that we just saw, it talked about how our body pH is around, on average, 7.35 to 7.45. And we want to maintain that consistent pH level, even if things are changing in our environment. So that idea of homeostasis, maintaining internal conditions. So buffers allow us to maintain that same pH range by resisting any changes in our pH by either absorbing or releasing hydrogen or hydroxyl ions. So we can see here is an example of our body's buffering system of our blood pH. So if we ingest something like, orange juice is highly acidic. So how do we prevent our body from becoming more acidic? So we need buffers that will release hydrogen ions or absorb hydrogen ions to stabilize that change in our pH. With our body system, our blood involves carbonic acid, so this H2CO3. So H2CO3 can break down into hydrogen ions and bicarbonate. And it can also break down into water and carbon dioxide. So if we have a bunch of excess hydrogen ions floating around, then that hydrogen ions are going to form or bond with the bicarbonate in order to form carbonic acid, and that's going to kind of remove it from that solution. That excess carbonic acid could then be converted into carbon dioxide, which then we can exhale to get rid of it. So let's go ahead and finish off this chapter, or this section of chapter 2, with some review questions. So which of the following statements is not true? So which one of these is not true? Water is polar. Is that true or false? Well, water is polar. Remember, it's a polar covalent bond that holds that oxygen and hydrogen ions together. So this is a true statement. Water stabilizes temperature. Is that considered true or false? Well, if we go back and recall specific heat, remember water has a very high specific heat. So it takes a lot of heat energy in order to allow the hydrogen bonds to break and allowing water to escape as vapor. So in a sense, water does stabilize temperature. If we think of areas that are close to the ocean, like cities that are close to the ocean, they tend to have mild temperature because water is kind of a buffer. It keeps the temperature pretty stable. Even and then if we go towards the continent center, like for example here in the United States, the Midwest is pretty far from the ocean, and so the temperatures are going to fluctuate at a greater capacity because it doesn't have this huge body of water to stabilize it. So water does stabilize temperature. That is a true statement. Water is essential for life. Well, you're made up of 70% water, so yeah, I'd say it's pretty essential for life. So water is, that one is definitely a true statement. So water is the most abundant molecule in the Earth's atmosphere. Is that true or false? Well, we talked about nitrogen early on, that is actually more abundant. So water is actually not an abundant in Earth's atmosphere. So this is the not true statement. It's not true. Here's another question for you. When acids are added to a solution, the pH should it decrease, increase, stay the same, or you have to test it to be sure? Well, remember from that video that we just watched with the teeter-totter thing? Okay, so when we have a decrease in the pH scale, we have an increase in the acidity, okay? So acids are added to solution, more acid, we're going to see a decline in the pH. So the pH will decrease. We call a molecule that binds up excess hydrogen ions in a solution, is that an acid, an isotope, a base, or a donator? So we call a molecule that binds up excess hydrogen ions in a solution. So it's taking in hydrogen ions. So if it's removing hydrogen ions from the solution, hydrogen ions will be removed, so it will become more basic. So that would be a base. Which of the following statements is true? So acids and bases cannot mix together. Is that true? Can I take something like, ammonia, which is, and I don't know, bleach and mix them together. So yeah, you probably don't want to do it in an enclosed space, but yeah, acids and bases, they can mix together. I mean, you can mix orange juice and soap and it'll mix together. That's, that's something that we can do. So, that works. That is this is a false statement. Acids and bases, they can mix together. Do acids and bases, they'll neutralize each other? So if we add acids and bases together, will they neutralize each other? Well, what happens? Acids, they'll release hydrogen ions into the solution, and bases will absorb those hydrogen ions. So they are essentially neutralizing each other. So this is a true statement. Okay? Let's see if the other ones are false. Acids, but not bases, can change the pH of a solution. Well, bases can change the pH of the solution by removing hydrogen ions, right? So that makes it more alkaline. So that's not true. Acids donate hydroxide ions, bases donate hydrogen ions. Isn't that the opposite? Acids donate hydrogen ions, bases donate hydroxyl ions. So that one is not true. So the only true one is that acids and bases will neutralize each other. So if we add an acid to the solution and equal amount of base to that solution with the same pH, it'll even itself out. So that is it for section 2.2 of our chapter 2 textbook, Openstax textbook. So I highly suggest that at this point you go back to the learning objectives that we went over at the beginning and see if you can answer those. Up next, I'm going to have a video on carbon, so that will finish off chapter 2. So don't forget to hit that subscribe button so you don't miss that video. All right, so once you're done, go ahead and take a closer look at the Openstax textbook for more further information.